first, and then we will also discuss the introduction on how to design a heat exchanger. So part of your requirement here is to design a heat transfer equipment. So this will be a great help for you to be able to understand the basic knowledge on heat exchanger design. So who among you have already seen a heat exchanger? Probably during plant tours or in the videos or some references. Anyone? Okay, so most of you haven't experienced seeing the actual heat exchanger yet, no? So, but I'll show you some examples here. So, but before that, I would like to inform you of our objective first. So, today we will study the basic principles underlying heat exchangers, uh, to identify the heat exchanger types, design characteristics, and applications, to introduce the performance parameters for assessing the efficacy of a heat exchanger, and to develop methodologies for designing a heat exchanger or for predicting the performance of an existing exchanger operating under prescribed conditions. So this is our objective for today. Okay, going back to heat exchanger. So as you can see here, this is the most common type, which is the shell and tube. Okay, so these are the basic parts. So we have here the shell, and inside it is the tube. So that's why it is called a shell and tube. So it is supported by a saddle here on the left and the right, then by a foundation. So there are control valves that regulates the flow of fluid. So there are nozzles where it serves as a distribution port for the fluid coming into and out of the heat exchanger. So we have here a nozzle on the top and bottom of the channel, as well as the shell also. So we have top nozzle and bottom nozzle on the shell. So there is a flange here, connected to piping, so by a bolt. So bolted siya sa flange. So we have here a tube sheet. This one is the tube sheet. So the end of the shell, and then connected by a flange to the channel. So this is the channel part. These two are the channel part. So channel 1, channel 2. So channel 1 is a bonnet type wherein it is welded to the shell flange, while the left channel, sorry, is a flange type, is a removable. So it is bolted. The cover is with bolted to the channel flange, so it can be removed. Okay, so but this one you cannot remove. So it depends on the type of the heat exchanger. Let's go inside. So this is the inside of the heat exchanger. So we have here, this is the shell, and inside are the tubes, and then we have a baffle. So the purpose of the baffle is first is to direct the flow. So imagine if there's no baffle, so the flow will be scattered all over the shell. So but if there's a baffle, so the flow will have a direction. So In this case, the baffle is horizontal cut, so there's a cut here. So when the fluid enters the baffle, the shell, so it touches the baffle, and now it has a direction. Yeah, up, down, up, down. So aside from providing direction or flow direction, the baffle also helps in providing a turbulent flow, wherein that flow is the one that we require in the heat for us to be able to have a higher heat transfer rate. So turbulent, if the flow is turbulent, it produces a high rate of heat transfer. Okay, so that's the another purpose of the baffle, and also it also holds the tubes. So the baffles are uh, provided with holes, so wherein the tube will fit on that holes. So according to the pattern that the standards are providing. So may pattern, we have a pattern, a tube pattern being considered here in designing in in preparing a tube layout. Okay. So we have the cover, tube sheet. Tube sheet is the one that holds the tubes in place aside from the baffle. So it is welded on the tubes. So I think I have a photo here of the tube sheet. Let me show it to you. Mm, there you go. So this is the tube sheet. Yeah, it's the one who uh, holds the tube. So it is welded here. The tubes are welded on the tube sheet here. So also the tubes are expanded inside so that it will touch the tubes sheet. So there will be no leakage. Okay, so we have the baffle here. It is horizontally cut, as you can see. So we will bolt this tube to the shell flange. So the shell has a flange, so it will be bolted here. Yeah. So tube sheets are usually made of a round flat piece of metal with holes drilled for the tube ends and a precise location and pattern relative to one another. So later we will have a short presentation on the different parts of a heat exchanger. Okay. So the process of heat exchange between the two fluids that are at different temperatures and separated by a solid wall occurs in many different engineering applications. So the device used to implement this heat exchange is termed as the heat exchanger. So the specific applications may be found in space heating and air conditioning, power production, waste heat recovery, and chemical processing. So that's the applications of heat exchangers. So as you can see here, we have a process flow diagram. So we have here a condenser, and we have a condenser and then a cooler. So let's say the working fluid here is the ammonia. So in order for the next process to occur, so the temperature of the fluid coming into this equipment is should be regulated. So if we desire the fluid, for example, the ammonia current temperature is 100 degrees, and the next process will require it to be 70 degrees Celsius. So we have to cool down the fluid, the ammonia. So it should enter the condenser, the cooler before it enters the another equipment. So in this case, the ammonia is being cooled by by a cooler. So that's the purpose of heat exchanger. So in your technical report, you will be required to include the process flow diagram. So wherein you will provide some information where the heat exchangers are being used. So I will provide instructions later on how you will proceed with your technical report. It is done in groupings. Okay. So types of heat exchangers, as you can see on our screen, we have different types. We have plate and frame. So we have double pipe, we have a shell and tube, and a spiral, and also an air cooler. So depending upon the applications and the requirements for the heat duty, so it it is the basis of the types of heat exchanger that we will use. So they are commonly applied in uh, heat exchangers. So they are devices used throughout industry for both heating and cooling process. So several variants of heat exchangers are available and find applications in a wide range of industries, including asthma heat exchangers, automotive. So I think you're all familiar with automotive heat exchangers. As a matter of, these are also what we call the car radiators. So as a matter of fact, I think Taji is driving now. So after after he arrived, so he can check the radiator of the car that he is driving. So yeah, it's an example of a heat exchanger. So in automotive, you also have brewery heat exchanger, chemical heat exchanger, cryogenic, marine heat exchanger, power generation, refrigeration heat exchangers. So there are so many types and of heat exchangers and in many applications. Okay. Uh, as a matter of fact, I have listed here some common applications, industry applications. For example, with corresponding type of heat exchanger. For example, shell and tube. It is commonly used in oil refining, preheating, oil cooling, steam generation, boiler blow down heat recovery, vapor recovery systems, industrial plant systems. Yung, the double pipe, the one that I showed you. Uh, so this one is a double pipe. It's a double pipe, so it is commonly used in industrial cooling processes, small heat transfer area requirements. So yeah, that's one of the consideration. And the plate and frame, so it's commonly used in cryogenic, food processing, chemical processing, furnaces, and closed loop open to cooling to loop water cooling. So condensers are used for distillation and refinement process, power plants, refrigerations, and heating, ventilations, and air conditioning. So yeah, we have different industries and applications of heat exchangers by type. So heat exchangers can also be classified on the basis of the direction of flow. So it can be a counter flow, a parallel flow, a cross flow, or a hybrid flow. Okay, so let me show you some of the uh, applications of heat exchangers and the types and the parts. So what I will show you is the shell and tube. So it's the most common.
Shell and tube heat exchangers
Can you see it now?
will look something like this. With this design, we normally find the inlet and the outlet for one fluid at the very end of the heat exchanger, known as the header. Then we have another inlet and outlet for fluid 2 on the main body, known as the shell. Inside the unit, we have the tubes. These bend and loop around to start and finish at the tube plate, which sits between the shell and the header. The tubes will usually also pass through some baffles, which are sheets of metal. We will see how these work in just a moment. The header, as well as the tubes, can be removed for cleaning, repairs, and maintenance. Inside the header is a sheet of metal known as the divider, or the partition. This separates the tube ends, enabling the fluid to flow into and then out of.
Okay, so as you can see, we have a pass partition. So it determines the number of passes on a channel side. So if it has a partition, so it means a 2-pass. So if the partition is divided into 4, so it has a 4-pass. So it's the one who determines who is the one that determines the number of pass the fluid will enter the channel.
Of the heat exchanger tubes. Fluid 1 will flow through the header, into and around the tubes, then back to the header. Fluid 2 will enter the shell and surround the outside of the tubes. The baffle.
So as you can see, this is an example of a counterflow heat exchanger wherein the channel fluid or tube side fluid is flowing opposite with the shell fluid. The shell fluid is coming from the top and then it goes to the bottom, while the channel fluid is coming from the bottom and then goes out at the top. So it's a counterflow.
Baffles will partially block the flow, which will force the fluid to turn multiple times. This creates a turbulent flow and ensures that fluid 2 mixes with itself, which ensures maximum heat transfer. For example, we might find this in a pharmaceutical factory with a boiler providing steam into the shell, which surrounds the tubes. A chemical product is then pumped through the tubes, and this absorbs the heat of the steam through the tube wall.
So as I have told you, I require to provide the process flow diagram for us to be able to know where exactly the fluid is coming in and out of the heat exchanger. So in this case, the steam coming in from the shell of the heat exchanger is from the steam boiler. Then it goes out in the condenser as condensate and then goes back again at steam boiler. Well, the chemicals coming in is from another source. It enters the channel and then eventually the tubes, and then goes up as high as with high temperature because the heat from the steam is being transferred to the tubes wherein there is a chemicals coming in. So there's no direct mixing of the fluid because of the tube walls.
So this product is going to exit the heat exchanger much warmer. Meanwhile, the steam will start to condense into a liquid and flow back to the boiler to pick up more heat and repeat the cycle. Additionally, these are used in refrigeration applications, like this industrial chiller. We have the water flowing through the tubes and the hot refrigerant in the shell. The water will absorb the heat of the refrigerant so that it can transport this to the cooling tower, where it will be ejected into the atmosphere. The water returns cooler to pick up more unwanted thermal energy from the chiller. We have covered how chillers work in great detail previously. Do check those out. I'll leave a link for you in the video description down below. Double pipe or tube-in-tube type heat exchangers will look something like this. This is similar to the shell and tube heat exchanger because essentially we just have a tube which runs back and forth a number of times between an inlet and an outlet. This is surrounded by a shell which has another inlet and outlet. A metal frame will hold the unit in place. Typically, these will all be made from stainless steel. One fluid will flow through the tube and another will flow through the shell. The two fluids are separated by the tube wall and transfer thermal energy through this tube wall. The different configurations result in different temperature profiles and heat transfer. In this design, the bend at each end isn't utilized for heat transfer, and heat can be wasted here. However, manufacturing this heat exchanger is cheaper and obviously easier. Other designs like this hairpin type heat exchanger, which are often found in oil refineries, will encapsulate the bend to fully utilize the surface area for heat transfer. This version normally uses multiple tubes to maximize the surface area and thus increase the heat transfer, although this will also increase the resistance. These are a fairly simple heat exchanger design and are very common particularly in food processing as well as pharmaceutical production. For example, we might have a dairy product flowing through the tube, and then we have hot water or maybe even steam flowing in the opposite direction through the shell, which will warm the product up to a certain temperature before it is mixed with some other ingredients and then bottled. Check out one of these videos to continue learning about mechanical and thermal.
Okay, so you have witnessed some of the examples and parts of a shell and tube and a double pipe heat exchangers. So how do we decide if the that for that type of heat exchanger to be used? So it actually depends on the following. So high or low pressure limits. So some heat exchangers are not uh, suggested for high pressure applications like the double tube pipe. So it's not recommended to use a double tube pipe in high pressure applications. So we are only using that for low pressure and low heat transfer applications. And then we have thermal performance. So we also consider this when we are designing a heat exchanger. So for example, if we want a heat exchanger with high performance, thermal performance, we will use a shell and tube heat exchanger. So tube pipe is also not ideal for a high performance, thermal performance heat exchangers. So temperature ranges, yes, it's also a good consideration. So product mix, pressure, liquid or liquid particulates or high solid liquids. So pressure drop across the heat exchanger, fluid flow capacity, cost. With regards to cost, shell and tube type have high cost compared to double tube pipe and other types of heat exchangers. So we must also consider that if we are not requiring a large thermal or heat transfer rate, so might as well we can consider using the double pipe heat exchangers. For cleanability, maintenance, and repair, so it depends on the application or the fluid that is using the heat exchanger. So some fluids are corrosive, So you must use a non-corrosive materials like stainless steel or hastelloy. So carbon steel is not a good material for sulfuric acid and other very acidic and corrosive applications. So yeah, materials is also required to consider when constructing a heat exchanger. So and the ability and ease of future expansion. So yeah, we must also consider the ease of future expansion. So as what you have uh, at what I have shown here, so there are different heat exchangers in series. So the reason is that it requires a possible expansion. It required an expansion. So previously, it possible that there are only 3 units, but as time goes by, as design progress, so it is increasing. So it's better to consider that when we are selecting a heat exchanger. So we can select shell and tube type if we want a future expansion, or also the plate and frame. So this one, plate and frame. So because uh, in plate and frame, you can add series of uh, plates. You can add series of plates if it requires extension or expansion. So I think I have here some photos of a plate and frame. Yeah. So yeah, fluid flow capacity, pressure drop across the heat exchanger. So these are some of the considerations when selecting the right type of heat exchanger. So how do you know if the heat exchanger that you use is correct? So we can check the standards for the heat exchanger, which is Tubular Exchanger Manufacturer Association Standard or TIMA standard. So it is a trade association of the world's leading manufacturers of shell and tube heat exchangers who have pioneered the research and development of heat exchangers for over 80 years. So they are the one who manufactures heat exchangers, and they are the one who made the standards. So this is for tubular type. Yeah, this one is a plate heat exchanger. So as you can see, we can add plates here because there are still spaces here. So if you require expansion, you can add just a series of plates here in this spacing. So it's very flexible. The plate heat exchanger is a very flexible type of heat exchanger as well. Okay. Okay, so I will show you another example of heat exchangers. The plate and frame. So it's also common in the industries.
How am I already underwater?
I'm in the same boat.
I'm in an actual boat.
I thought Grammarly just fixed grammar. They make boats now?
It's more of a metaphorical
Apologies
boat.
for the ads.
Because I've been using Grammarly's AI for years to keep me high and dry. Try it. Grammarly can look through your writing to make it easier to understand. See? Shorter,
Whoa,
clearer,
Cool.
And better. Now people will get what you're trying.
So how does it work? Well, Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be looking at the plate heat exchangers. They're often referred to as PHEs, PHXs, or sometimes just HX or HEX. Now, plate heat exchangers are very common. They are used extensively in building services and manufacturing. The reason they are popular is because they are very compact, they're very efficient, they're easy to service, they need very low maintenance as well. Their purpose is to transfer thermal energy from one fluid in one system to another without the two fluids mixing together. For example, in building services, you might want to transfer heat from a primary loop connected to a boiler over to a separate secondary loop, or maybe in a district heating network. Or in manufacturing, you may want to cool down some oil and use water to cool that down, but obviously you don't want to mix the oil and the water together. Now, if we pulled one of the heat exchangers apart, we're going to have a look at some of the main components here. So we've got the end plates here, or the front and back cover, and these are made from usually a mild steel, and they're very strong. They're there to hold everything together. Then we've got the nuts. These attach obviously and tighten up onto the tightening bolts. The tightening bolts, they fit in, there's some grooves in there, and they'll run the entire length of the heat exchanger. And the bolts are tightened on these, and that will compress all the plates together and squeeze the gaskets against the plates to make the heat exchanger completely waterproof or leak proof. And then wedged in between there, we've got the plates where the heat transfer occurs, and we've also got the gaskets which sit in between the plates, and that's what gives it the seal. Larger heat exchangers will also have this supporting bar at the top and the bottom, and you can see here that the case and the plates, they just slide along there, and there's various ways that they can come off. Either they twist, these ones will be too big to twist off, but there's a section removed at the back where these will just drop out. But the smaller ones, these will just slide in and out. Now you can see a real plate, a heat exchanger plate there on the screen. Now these are typically made from steel or titanium, and you can see they've got this pattern grooved into them or stamped into them. These patterns are going to strengthen the plates. Obviously they're incredibly thin, and they're also going to increase the heat transfer surface area, as well as creating a very turbulent flow inside them. So it's not smooth. All the water has to rubble across these and come out very rough and turbulent. Now between the plates, we've got the gaskets here, just this rubber gasket, and that is attached to the face of the plate. And the purpose of the gasket is to ensure a tight fit and to prevent leaks. The gasket also allows or prevents the flow of fluid into the sheet. You can see here, so in this section here, we've got the rubber seal coming across and a double seal on this one, so that no fluid in this can leak out or flow in, as well as this side, whereas here there is no gasket there, so the fluid, if it entered here, it could flow down and come down and enter into this one here because there isn't anything there. Same as this one, the fluid can only come out of here and travel up and then into this section here, into that hole. Now you'll probably notice that the tightening bolts are, they're actually, they extend far past the heat exchanger. That's for a few reasons. One is obviously to be able to fit all these plates and etc. on during the installation or during maintenance, but also this gives you the ability to extend the plate heat exchanger in future. So this one here is actually from a district heating network, and at the moment the building's only half complete and they're expecting to double the building size, so they've allowed extra bolt lengths to be added, and that means that the plates can be added and this heat exchanger can grow with the demand. Now there's a couple of ways that the plate heat exchanger can be piped up. This is the most common version, and the version that we're going to be looking at today. That is where the inlets and outlets are all on the front plate. So the fluids will enter, flow through their channels, and then make their way back to the front plate. The other version is where the fluids, one of the fluids enters through the front plate, and it passes through there and then makes its way, and it will then exit through the back plate, as well as one of the fluids will enter there as well. Now this version here, the first version, is the most common version, and that is because you don't need to alter the pipework if you need to extend the plate heat exchanger in the future, whereas with the second version here, all the pipework that's connected will have to be removed and remade to fit depending on how far you extend your plate heat exchanger. So it's not really so practical. That is why this one is far more common. And you can just see in all these examples here, that is exactly what's happening. So the flow and return are happening on the front plate there. So how does it work? Well, we've already seen that if you remove some of the seal, then the fluid can flow through there. So if we stack a number of plates together, then you'll see it forms this this channel, this pipe-like feature flowing through all the plates. And then we can add the front and back plates onto there, and then we get these channels where the water can, or the fluid, whatever you've got, can then flow through certain plates, and it can't flow through other plates. And let's just see an example of how this would work practically. So if we open up the heat exchanger again, now you can see here that the gaskets is oriented differently on the alternating plates there for the heat exchange. So this one here, you can see a fluid in this pipe would not be allowed to pass through, or this one, and this one it would, so it just alternates vice versa all the way through. And so if we pass one fluid through there, you can see it entering through this top port, passing all the way through. It can't pass through this one. There's a seal there. It gets to the next plate. Oh, there's no seal there, so we can pass through there. Can't go into this hole, but it can get into this one because there is no seal. And so all these will pass through, collect up, and make its way back out. Now the same thing is going to be happening with the other fluid we're passing through. So you can see here we're passing a hot fluid through, and this one is entering through the bottom port, coming along. It's getting to the plates. Some of them it can pass through, so it will. Others it cannot leave that pipe, so it will not. And it will just pass through all the way until it creates that loop and exits. So if we mix these two fluids together, what's going to happen is the cold fluid is going to enter, pass through, and then on the other side of the plate is the hot fluid. So that is going to take some of that heat away. So the cold fluid will warm up, and that will leave as a much warmer fluid. And the hot fluid that comes in is going to cool down because it's going to give up some of its heat into the cold stream, and then that will leave as a much cooler fluid. So if we just look at a very basic example of how this is working, let's just say we've got a few plates here, and we've got a cold channel, hot channel, and another cold channel. Now if we let the hot fluid enter into the channel there, and as that happens, heat is then going to conduct through into the plates because they are touching, so that heat will then pass through and warm up this plate. And if we then pass the cold fluid into the cold channels, then some of the heat in those plates which have been heated up will start to cool down because some of that thermal energy is transferring over into the cold fluid. That's through conduction. And as that happens, the cold fluid begins to warm up, and obviously the hot fluid is going to start to cool down. So then the heat exchanger starts to equalize out, and that means that the cold fluid is going to exit warm, and the hot fluid is going to exit cool. And that temperature gradient is going to then vary through the heat exchanger, through the plates, and also through the fluids which is conducting the heat. So when you combine all of this together, that is how you get the heat transfer occur in the plate heat exchanger. Now you can also notice that these fluids are flowing in counterflow. Now that is the best configuration for the most effectiveness, because the log mean temperature difference, the LMTD, is at the greatest. We'll have a look at what that means in another video. This video is just for you to understand how it's working and why it works. I'll just give you a real world example of a heat exchanger here as well. So this is a German heat exchanger, as you can see. Written down here, but you can see this heat exchanger here can provide 1500 kilowatts of thermal energy, and has a transmission area of 29.3 meters squared with a flow rate of 42,000, almost 43,000 liters per hour. It will also handle up to 100 bar on each side of the plate. So you can see these things are very powerful, and they're very efficient and very compact in how they work. Now, if you do have one of these in your buildings, please also remember to insulate this as it's much more energy efficient, and keep the plastic threads, plastic sheets on the threads to protect them from damage. Otherwise, you won't be able to get these nuts.
Okay, so that's plate and frame. So another type of heat exchanger. So what you have seen earlier is the counterflow, yung flow ng ating fluid, wherein they mentioned that wherein it is mentioned that the if the flow is counterflow, so we have a high lag mean temperature difference. So with regards to lag mean temperature difference, we will discuss that on our future discussions regarding the heat exchanger analysis. So this is an example of the uh, tubular type. So wherein I have already shown you earlier. So this is also a counterflow. So as you can see, the flow is the flow from the shell. The flow of the fluid on the shell is opposite on the flow of the fluid on the tube side. So the flow of the shell is downward, while the fluid that comes inside the tube is flowing from bottom to top. So it's a counterflow. So shell and tube heat exchanger, aside from the from uh, plate and frame, is also the most common type of heat exchanger used in oil refineries and other large chemical process plants. So as its name implies, this type of heat exchanger consists of a shell and with a bundle of tubes inside it. So these are the common parts. We have the shell, tube sheet, head, gaskets, mounting, baffles, and tube bundles. So when we say tube bundles, it is the bundle of tubes with including the baffle and tie rod. Tie rod is the one that holds the baffle. So this is a YouTube type shell and tube bit exchanger. So it's a two pass on the shell, on the channel as well as and the channel rather because there's a pass partition here. So it's not when we are talking about the cleanability. So mechanically, it is hard to clean a YouTube type because of the bending of the tubes. So chemical cleaning is usually applied when uh, considering the cleanability. So we have a straight tube. So this one is easy to clean mechanically. So the tube is straight. So from starting from here, you can insert a water jet from here going to outside. So we'll just have to remove the channel on both sides. So for us to clean this straight tube. So this is a one pass tube side. There's no partition on the channel part. So the flow is also a counterflow because of the opposite direction of the tube side fluid coming in and shell side fluid coming in. So this one is a two-pass tube side straight tube heat exchanger. So straight tube siya, pero meron siyang partition. So two-pass siya, no? So two-pass on the channel. Okay, so we have tube layout patterns. This is based on the TMA standard. So triangular, if we need to accommodate more tubes. So it produces also high turbulence and limited to clean shell side services. So we are just like this one. So this is triangular. We can accommodate more tubes here because of the spacing is less compared to square. There is a large space. However, it is hard to clean mechanically. So because of the spacing, very small. So unlike this square type or rotated square, it can also be rotated as well. With the square one, so cleaning is required. When cleaning is required, it is recommended to use a square type. So it produces a low turbulence compared to triangular and accommodates low number of tubes. Yeah, it is advisable to use this tube pattern for some applications where it requires cleanability. So how about this one? I have some pictures here. What type of tube pattern is this? Let me show you some. Yan. So anong tube pattern to? What tube pattern? Anyone? So it's a rotated triangular, as you can see. Yeah, so that's rotated triangular. Yeah, so yeah, that one is rotated triangular, as shown here. This one, rotated triangular 60 degrees. So sometimes, we also have other components such as channel partition plates. So for heat exchangers with multiple tube passes, the channels are pitted with flat metal plates which could divide head into separate compartments. So shell baffle. So sometimes the baffle is cut like this one, horizontal cut. It's a horizontal cut. So we have longitudinal flow baffles, impeachment baffles, of orifice, double segmental, disc and donut. So these are some of the baffle types. So depending on the application. So disc and donut, so ito yung disc, ito naman yung donut. Yan. Minsan full baffle siya, no? Full baffle. So you will be the one to decide what type of baffle you will use. So it depends on the standards, the TIMA standards. Tie rods are circular metal rod screwed into stationary tube sheet. So I think tie rod yung nag-hold sa baffle. So we have front head type, we have A type, B type, and C type. So these types are based on the TIMA standard. So we have here the TIMA standard, this table. So I'll just show you. So these are the tables. So stationary heads. If the first column is stationary head, the second column is shell types, and the third column is the rear head. Okay, so if it says that the thema type is AEU, so meaning it's a removable channel and cover with one pass shell with a YouTube bundle. So AEU. We have here some example. Yeah. So thema heat exchangers are examples are so BEM, for examples, we have a bonnet integral cover, one pass shell, and fixed tube sheet bonnet. So it's a combination of the stationary head, the shell, and the rear head. So BEM, so this one, BEM is here. So this is B, bonnet integral cover. E is a one pass shell, and M is, I think M is a fixed tube sheet. So fixed tube sheet, M. Okay, so that's BEM. Next example, we have AEM. So almost same as the previous one. The only difference is the head. So we have here removable. This is removable head A. So removable channel and cover. So this is A. And then we have E is the shell, one pass shell, and then M, bonnet. Ah, yeah, this one, bonnet. So next one is AES, sorry. Almost same as the previous one, A, one pass shell, removable cover on channel of the left channel removable cover. So one pass shell, and then we have floating head. So S is floating. When we check here, S is floating head with backing device. So it's a floating head. So that's AES. Next one is, so this is a kettle type. So it's AKU or kettle type A, removable head. Uh, then K is kettle, and then U is YouTube type. So as you can see here, so this is kettle type, kettle shell, kettle type reboiler, and then U is YouTube bundle, and then A is removable channel cover. So just a combination of the three. So we have combination of stationary head, shell type, and rear head. So that's the thema designation that we are referring to. It's thema designation. Okay. So baffles are used to support tubes and enable a desirable velocity for the fluid to be maintained at at the shell side and prevent failure of tubes due to flow-induced vibration. So there are two types of baffles, the plate and rod. So plate baffles may be single segmental, double segmental, or triple segmental. So anything, yeah. So pwede siyang horizontal cut, pwedeng vertical cut. So we have tube sheets. So it holds the tubes in place. So they are usually made of a round flat piece of metal with holes drilled for the tube ends and a precise location and pattern relative to one another. So tubes are attached to the tube sheet by pneumatic or hydraulic pressure or by roller expansion. So tubes are drilled and reamed and can be machined in one more grooves or more grooves. So this greatly increases the strength of tube joint. So just like this one, so it can either be rolled here. So when we roll the tube here, it expands. Then eventually it expands. So it will touch the tube sheet hole. So there will be no leakage. Okay, so yeah. So these are bundles. Yeah, bundles includes the tube sheet, the tubes, and the baffle, as well as the tie rod. Okay, so that's for the parts of heat exchanger, shell and tube. So let's go to other types of heat exchanger that I have also mentioned. So we have the double pipe heat exchangers. So it is also known as the concentric heat exchanger. So in this heat exchanger, the fluid to be cooled or heated passes through the tube, yung green color. So fluid to be heated is passing through the tube, and then there's another tube outside or on the red one. So there's a fluid flowing outside, which is a heated fluid. So when as you can see, the flow is counter flow. So the fluid on the green or inside the tube is flowing opposite the fluid on the pipe or outside the tube. So there will be a heat exchange. So advantage of this type is cheap for both design and maintenance. So ang disadvantage niya is low efficiency and requires large space. So as you can see here, this is an example of a double pipe. So it requires a large space if especially if you will use a high thermal uh, if your requirement is high heat transfer area, so you will require a large or many series of double tube pipe. So it requires a large area also as well. So this double pipe heat exchanger is uh, suitable for heat recovery, for preheating, and effluent cooling. So next type is the air-cooled heat exchanger. So an air-cooled heat exchanger or air-pin cooler is a device for rejecting heat from a fluid directly to ambient air. So ang obvious advantage, the obvious advantage of an air-filled cooler is that it does not require water. So which means that the plants requires large cooling capacities need not be located near the supply of cooling water. So if there's no supply of cooling water, especially on the remote areas, so this air-cooled heat exchanger is the best option. So although it has some disadvantages, so let's go first with advantages. So air piping system is not required, larger limit of air supply volume, no fouling or scaling outside the tubes. Yes, because there's no corrosion. So more economical, easy maintenance, no possibility of contamination of or from process flow. And in case of electrical malfunction, so 30 to 40% cooling is done by natural draft. So disadvantages are cooling level is limited by ambient temperature alone. So we cannot use other cooling mechanism. So more electrical equipment is needed to power up the fans and blowers. Just like this one, so there are many electrical components required to power up these fans. So higher initial costs, I agree with this, and leakage is more dangerous or fire hazard. So more sensitive to rains, yes. Okay, so these are the parts of an air-cooled heat exchanger. So this is a first draft. So there's a fan below. So the tube bundle. So this is the tube bundle. So we have the tubes here, and then we have a nozzle, and then header, and then we have 4 is plenum, 5 is the fan, so 6 is fan ring, 7 is inlet bell. I'm not sure about this. And then drive assembly, and then or yung motors. So column support 9. So yan yung parts ng air-cooled heat exchanger. Okay. So an air fan cooler consists of the following components: one or more tube bundles of heat transfer surface, air moving device such as fan or stack, So unless it's natural draft, a driver and power transmission to mechanically rotate the fan. So dito gumagamit tayo ng force convection to cool down the fluid. So may fan tayo dyan. So magkakaroon tayo ng bulk motion of fluid. So a support high enough to allow air to enter beneath the AC at reasonable rate, optional header and fan maintenance walkways and ladders, optional louvers for process outlet control, and optional variable pitch for fan hub for temperature control and power saving. So these are auxiliary parts for the air-cooled heat exchangers. So far, you have already the idea of the different types of heat exchanger, right? So hopefully it will help you to uh, do your technical report easier. So I will send the instructions later. It is done per group. Okay, so we have another. We actually have different types of heat exchangers here in this module. So next one is the spiral heat exchanger. So spiral heat exchangers may refer to a helical coiled tube configuration. So we have efficient use of space because the design is very compact, as you can see. So they can be easily cleaned. And spiral heat exchangers is a coiled tube arrangement with two channels coiled on one around and another. So these two channels operate in a counterflow arrangement, offering excellent turn-down ratios while optimizing flow patterns, which in turn enhance heat transfer. So sino sa inyo nakakita na ng katol? So just like this one, so it's like a katol. So we have here the fluid on the fluid one is entering here, then the red one, so it goes circular. So until it reaches the outlet. The fluid 2 is coming from opposite side here, and then it also circulates. So the fluid one is actually uh, hot fluid. So goes uh, as it exit the exit point, so it is being cooled down. Other Conversely, the fluid on the other side is a cold fluid, and then it is eventually heated up because the heat is from the fluid one is being transferred to the fluid number two. So it exits the heat exchanger in opposite direction. So it's a counterflow as well. So this is the spiral heat exchanger applications. So pasteurization, recuperates systems, sludge treatment, and thermal depolymerization. So these are some of the application of spiral heat exchangers. So this is the spiral. Okay, so we also have heat exchangers that are large. These are the special types. So are commonly used for heat exchangers in chemical plants. Okay, so maintenance of heat exchangers. So five major steps are involved in cleaning a small heat exchanger in shop. So we have disassembly, cleaning, testing for leaks, inspection and repair, and reassembly or final testing. Okay, so how do we check if there's a leakage on the tubes? So we will use the non-destructive testing. So such as uh, hydro testing, pneumatic testing, and gas testing. So these are what we call the non-destructive testing or NDT. So we have hydro test. The water is used as testing media. So the test pressure is 1.5 times design pressure. It came from the ASME. So it varies depending on the project specification. So pneumatic one is the fluid is air. So air is used as a testing media. So test pressure is 1.25 times design pressure. And then lastly, the gas test, it's any gas other than air is used, such as nitrogen. Okay, so going back, yeah, so cleaning. So kanina, earlier we have discussed the consideration when the tube sheet requires cleaning. So it can be mechanical cleaning, so shell side or water jetting, or manual scrapping. So tube side water jetting or scale cutters, brushes, lances for tube. So chemical cleaning, they are using carbon tetrachloride. So it is used to dissolve scales which not be scrapped mechanically. So have you seen some scales? So these are example of scales that we are avoiding as much as possible because the scales reduces the rate of heat transfer, and there is also a reduction in volume because of the plugs caused about by the scaling. Also, if the rate of heat transfer is being reduced, the efficiency of the heat exchanger is also being reduced, and thus increasing the differential pressure. So solution is to use a chemical injection and exchanger cleaning or hydrojetting, steaming or chemical washing. Pero the best solution here is prevention. So how do we prevent heat exchanger against fouling or the formation of scale on the heat transfer surfaces in the heat exchanger? So do you have any idea how to avoid this fouling? So we can avoid this during design stage. So we must use the correct material. So as I have said, if the uh, material is if the fluid is corrosive, so we must use the correct material. So either we can use a stainless steel or we can use a lining or surface roughness or surface finish rather or lining to avoid corrosion. So it's not enough that we specify a corrosion allowance, but also we must specify the correct material. Okay, so that's for fouling. So also leakage, as you can see. So the effect of leakage in the heat exchanger is it reduces the heat transfer rate and contamination in the product. So yeah, it's very important that the product should not be contaminated. So it also decreases in efficiency of heat exchanger. So the best way to avoid this is to replace the tube. So that's the only way to replace the tube. Okay, so corrosion, these are corrosion. So ang solution na lang dito is tube replacement or surface coating. And this one is thermal shock. So it happens when there is a tube leak or damage in expansion bellows. So it happens thermal shock. So to avoid this, we must follow up standard operating procedure. Okay. So do you have any questions so far? Uh, can you catch up on our discussion? Can you still catch up on our discussion? Okay, so let's move on. So we have here the software. Let's go to software. for heat exchanger design. So heat exchanger design software. So the most common software that we use is the HDRI. So in HDRI, so provides advanced experimental research to the oil and gas, chemical and petrochemical industries. So here we can estimate the surface area and the size of the heat exchanger by using the HDRI. We will just input the parameters such as temperature, heat duty, and also the fluid properties. So if we input the fluid properties, we can use HDRI to calculate uh, for the surface area. So by the way, meron akong ginawa. I have done similar but in Excel form. I will share to you. So who among you have knowledge on uh, Visual Basic? Anyone? Visual Basic? So because I prepared some computational tools that you can use, but however, so the one that I prepared is very basic. So it will be better if you will provide some visual basics on this. So who among you does know how to use Visual Basic in Excel? No one? Anyway, so this is the one that I prepared. So for example, we are given the fluid properties. So we'll just input the temperature, the air density, viscosity, heat capacity. So this can be found on the what you call this table on your table. So also this thermal conductivity. So if you have these properties, we can calculate for the log mean temperature difference LMTD automatically. So this can be this LMTD is the one that will lead us to determine the actual surface area required. And if we know the actual surface area required, we can check the number of tubes required and the diameter of the tubes. So yeah, that's a great help for you to design a heat exchanger because you will no longer compute it manually. So the problem here is that it's not user friendly. So that's why what I'm asking if some of you are able to improve this calculation using the Visual Basic. No one? So okay. Anyway, so I will provide if just in case you know how to use this Visual Basic, so I will provide additional points for you. Yeah, if you can help me improve this calculation, so we can use it when we are preparing for a technical report. So yeah, there's 6 steps. So first step is to input flows, conditions, and properties data for shell side and tube side. The next step 2, is to input tubing, OD, and length that can be trial and error. Step 3, step 3, start configuring the heat exchanger, begin with the assumed overall heat transfer coefficient at this point. Step 4 is bundle and shell diameter. So yeah, it's a trial, can be calculated. Yeah, I provide formula here. So next is tube side and heat transfer coefficient. We have the Nusselt number, Prandtl number, Reynolds number. You can find it here. So we have step 6 is shell side heat transfer coefficient. Okay, so the pattern is here. What pattern? Tube pitch, baffle spacing, area of shell, equivalent diameter, volumetric flow rate, shell side velocity, shell side Reynolds number, Prandtl number, segmental baffle cut. So yeah, and the overall heat transfer coefficient can be calculated. So if we know the overall heat transfer coefficient, we can calculate the size of the heat exchanger. So that's step 6. Okay. So yeah, that's one option. And another option is to use the HDRI. So, but I think no one of you have copy of HDRI software. It's usually used in the industry. HDRI. So I have a copy here, but it's not original. So there will be a copyright issue. Okay, so another software is Decompress. So it is common in industries. So the purpose of this software is to calculate the strength of the shell. So based on ASME standard. So we will provide some fatigue assessments here. Same as PV Elite. So this is also vessel and heat exchanger design analysis and evaluation software. Okay, so we have capabilities, vessel design and analysis, exchanger design and analysis, tube sheet design and analysis, and rectangular and non-circular vessel analysis. So, and lastly, we have the ANSYS software. So this is free. I hopefully you already have installed this software. So because this will be used, you will use this during modeling and simulation of heat exchangers. So it optimizes heat exchanger design for performance and energy efficiency, material selection, durability, and life prediction under harsh conditions. So please try this software. So you have free access using your G Suite. So please use this when you are preparing your technical report. Okay. So yeah, and we have the basic calculation. So we will discuss it on the next meeting. Question. So question, do you have any questions? Yes, Alvin.
Sir, good afternoon po. Hindi naman po about sa topic. Ang tatanong ko lang po is about sa groupings. Kailan daw po kaya or sino daw po kaya ang mag-group at saka kung ilanan daw po?
Ilan nga tayo? 45 ba tayo? 48?
47 po, sir.
47? Okay, so 47. Hmm. So we have 12 groups. I know. Divide by 9 groups. So 2 groups with is composed of dalawang 6, and then the rest, the 7 groups composed of 5. So
Sir, 48 daw po pala kami.
48. So 48. So we have 8 groups. So we composed of 6 members. Okay. So please, I will allow you to decide under your groupings. Kayo na lang mag-decide ng groupings. So, pa-send na lang ng list pag meron na. Magme-message din ako sa GC.
Okay po, sir. Thank you so much po.
Okay, so do you have any questions? Okay, so let's see each other again next meeting. So I will distribute the result of your exam. So hopefully, you will triple your effort so that you will not take again this course in the next semester. Thank you.